Points were raised at the end of the talk yesterday. One was, or during the talk, one was the replacement of del squared by box in an attempt to make a relativistic version of Newton's laws. And the person, I looked it up, is Nordstrom. I think it was about 1915 or thereabouts. Nordstrom's name will crop up later in the class because he was, together with Reissner, the discoverer of the charged black hole solutions. So that answers that question. A more subtle question was to do with the equivalence principle and the use of the word accelerated and unaccelerated. Was causing some confusion, and rightly so, I think, because it is confusing. But let me just say a few words in the hope of resolving the confusion. We had the fellow in free fall. And we had the fellow on the flat Earth. And this one feels a gravitational field because he sees the baseball drop to the ground. This one doesn't. And so if he were writing down his field equation in coordinates, so he's observer O, let's call him, with coordinates x and t, he would write down the Newton's law like this. Whereas observer O prime with coordinates x prime, t prime would say x prime equals x minus 1/2 g t squared. T prime equals 0. And so according to him, the laws of physics are if they were in special relativity. So the confusing thing, at least I find it confusing, is you think he's falling, he's accelerating in the sense that his speed is getting greater as he falls. But he's not accelerating in the sense that there's no force in his equation. This fellow is accelerating, feels the acceleration. So when Einstein says, that was the inhomogeneous case. That was the homogeneous case. In the inhomogeneous case, this is only approximately true, that you can cancel this term. You can do it in a sufficiently small region, but you can't do it globally. But that's what, when we refer to the locally inertial system, it's this that we have in mind. The freely falling system is, in this context, the unaccelerated. When the words unaccelerated are used, it means no acceleration term in the equations. So freely falling is unaccelerated for these purposes. Is that clear? Or has that confused you even more? Yes.
I just want to know, when you discussed the version of the equivalence principle that describes inhomogeneous fields, I believe you said that there is an inertial coordinate, a locally inertial coordinate system. What did you mean by inertial in that case?
One where the laws of physics are as they would be in special relativity, in the absence of a gravitational field. And you can do that locally, but you can only do that in a sufficiently small region in the inhomogeneous case. So freely falling, inertial, unaccelerated. What we mean is how you would have written it if you hadn't known anything about gravity. Just looking about special relativity, that's what we mean. And you can always go to that local coordinate system. You can always do that locally. When we come to, as we are going to do shortly, the geometrical interpretation, I will give you the same argument in the language of metrics, Christoffel symbols, and Riemann tensors. Were there any other questions from yesterday or anything about anything? Okay, so we'll move on. And the final motivation was general covariance. Well, let's talk about transformation of coordinates first. And we can start using Weinberg's notation, B2 psi alpha ds squared equals 0. So for Weinberg, psi alpha is the freely falling coordinate system. And ds squared is eta mu nu d psi. Well, let's reserve alpha and beta for the freely falling system. Now he wants to transform to some general system, which is not freely falling, with coordinates x mu. So the size will be functions of the x's. And we can rewrite this equation as d by ds, d psi alpha partial, d psi alpha, dx mu by ds, which is d psi alpha dx mu d2 x mu ds squared plus d2 psi alpha dx mu dx mu ds dx mu ds. Now, if we multiply this by dx lambda d psi alpha, and use the fact that you say I alpha dx mu dx lambda dx psi alpha is delta lambda nu.
Well, I said that the ds is called the proper time, but I'm actually not sure why it's called proper time or why it should play the role of time in that equation of motion.
Well, we want the equation to be relativistically invariant. Time, the t coordinate, is not a tensor, it's just the component of a vector. So we want our equations to be Lorentz invariant.
So it seems like the motivation for...
Well, again, why it's called the proper time is a bit like why those forces were called tidal. It's a historic nomenclature that we retain to.
So the reason why df squared is playing the role in that equation that time would play in the version of Newton's law, Newton's second law that we're familiar with, is df squared is relativistically invariant. We want an equation that's relativistically invariant.
Yeah.
But
I mean, what you should find, if it's all consistent, is that in the limit where the velocity of light goes to infinity, your relativistic equations should reduce to the familiar Newtonian equations.
So I was just wondering, it seems like a useful motivation to see why it would make sense that something relativistically invariant would be in the denominator there, but that doesn't really seem like a physical reason for why something that's a force equation would have the proper time in the denominator playing the role that we usually ascribe to time.
Well, here, yes, it often happens that the mathematics leads the way to the physics, because mathematically that's our only choice if we want to be relativistically invariant.
So if I can think of the normal Newton's second law in terms of time, in terms of graph and my everyday experience, is there some way to physically understand the significance of that apart from by reducing it to the low velocity?
Well, I don't know if this is satisfactory to you, but to me, when we have a new law of physics to incorporate, I don't have any prejudice about what the equations are going to look like, but I do insist that they reduce to the equations we're familiar with when the novelty is removed.
So I should sort of accept that as a postulate?
I mean, when you introduce something new, what's right and what's wrong? It may meet your expectations or your prejudices, it may not. So I don't know whether to be surprised by that or not surprised, but so long as it reduces to everything I'm doing reduces to Newton's law in the appropriate regime when the velocities are small, which mathematically is equivalent to sending c going to infinity, I'm reassured that I'm not doing something totally crazy. We'll encounter the same surprise, if you like, when we go to general relativity, and we'll see equations that are dictated by the mathematics, by the requirements of general covariance. And I guess in some cases we'll be surprised, in some cases we won't. But we'll insist, once again, that when the velocities are small, we recover all the rules of special relativity. And when the gravitational fields are weak, we recover the Newton's laws of gravity. We can't really ask for much more than that. So let me continue. It often happens, I mean, just speaking as a theoretical physicist, it's a matter of curiosity, that often you lose sight of the physical interpretation for a while. And you just take your hands off the steering wheel and let the mathematics take you wherever it takes you.
I was just wondering.
And if you can keep track of the physics, so much the better, but it's not always the case. Sometimes you have to do the calculations, and only later you figure out what it all meant. Sorry, did you have another question?
I was just trying to make sense of this whole thing since we have been writing a lot of symbols, and I was wondering where they came from, what significance I should ascribe to them, why I should be copying them.
And the only answer I can give you is Lorentz invariance, is what we're insisting on, rightly or wrongly. Nothing experiments indicate rightly. And once you've done that, the equations follow inexorably in the symmetry. So that's if you're asking yourself, why am I writing this equation? It's because of Lorentz invariance. But now we're going to depart from inertial frames. We're going to go to general frames, X. And now that you'll see that what looked like a Lorentz invariance equation is going to turn into something which is unfamiliar. And now I'm introducing a new symbol, capital gamma, with one upstairs index and two downstairs indices. And this has a name. It's called the affine connection. And don't ask me why it's called the affine connection. It's defined to be dx lambda by psi alpha, d2 psi alpha, dx mu, dx mu. And physically, if you want some sort of physical feeling for this, this extra term is something that is telling you that the particle, or whatever it is, light ray particle, is no longer following a straight line. This extra term means that it's been following a curved trajectory. Similarly, the infinitesimal distance which we can write now looks like this. And this G mu has a name. It's the metric tensor. And it's symmetric. Swap the indices around and it doesn't change. We can also define the inverse of the metric tensor. then you can show that G nu sigma G kappa nu is delta I've got it written down wrong in my notes, so let me write it correctly. G mu nu G nu rho is delta mu rho, which tells you that G with upstairs indices is the inverse of G with lower indices. That follows from the definition. So, this is where the geometry is beginning to sneak in to the picture. We've decided that the motion of a particle in these arbitrary coordinates requires the introduction of a space-time dependent metric tensor G mu nu and a term which tells you about the acceleration, which is given by the affine connection gamma lambda mu rho. Now, these two quantities are actually related because if we differentiate with respect to x lambda, and I'm now going to introduce a notation which one finds in some of the textbooks. And instead of writing partial derivatives, we write commas. So the vector with a comma mu means differentiate with respect to x mu. And here it means differentiate with respect to x mu. And so differentiating G means G mu nu comma lambda is psi alpha comma mu lambda psi beta comma mu. And eta is a constant, so that just stays the same. Plus psi alpha comma mu psi beta mu lambda into alpha beta. And we recall that psi alpha comma mu nu is gamma lambda mu nu psi alpha comma lambda. So G mu nu comma lambda is gamma rho lambda mu psi alpha comma rho psi beta comma mu beta alpha beta. And keep track of these indices. If I make a mistake and they don't add up, let me know. The indices on the left have to match the ones on the right, and if they're repeated, they're summed over. And we end up with an expression that involves just gamma and G. Which we can rewrite G mu comma lambda plus G lambda mu comma mu minus G mu lambda comma mu is twice G kappa mu gamma kappa lambda mu. So if we multiply by the inverse, we can solve for gamma. And this is an equation you'll be seeing over and over again if you do general relativity. Which gives the gamma in terms of the first derivative of G. In fact, in the textbooks, you'll sometimes see that this particular combination is sometimes written like this, in which case it's called a Christoffel symbol. Strictly speaking, an affine connection is slightly more general than a Christoffel symbol. I've glossed over the difference here. For today's lecture, they're the same thing. But in subsequent lectures, we'll see how you can have connections that are not Christoffel symbols. Now, this gamma is the quantity that entered into our equation. It tells us how much the trajectory is curved. And so you can ask, this is a fairly important equation, can it be derived from a variational principle? And the answer is yes. And I'll leave this as an exercise for you. But let's consider 2 points, P and P prime, with some trajectory x mu of little p, capital P prime, where little p is a parameter. And we define the proper time elapsed as the particle travels from P to P prime is capital T sub P, P prime equals integral P to P prime ds dP dP, which is the integral from P to P prime square root G mu nu dx mu dP dx mu dP integral dp. Now, if we now vary that, if we now vary the path from x mu to x mu plus delta x mu, we can see that the path followed by the particle extremizes the proper time. Such that delta x mu equals 0 at p and p prime. So this is your exercise. Delta p, p prime equals integral p to p prime d2 x mu ds squared plus gamma mu rho sigma dx rho dx sigma g lambda mu delta x lambda ds. So, if we extremize the proper time, we find the equation. By the way, this has a name. It's called the geodesic equation. And any path that extremizes the proper time is called a geodesic. So, Einstein said coordinates play this role. Going to arbitrary system of coordinates requires a metric tensor and an affine connection. And this led him back to where he started from, which was, why should the laws of physics be the same in inertial frames and not in general frames? And he concluded that indeed the laws of physics should be the same in all frames of reference, whether they're accelerating, rotating, whatever they're doing. And this led him to the principle of general covariance, which can be embodied in two statements. So a physical equation holds in a gravitational field if 1, the equation holds without a gravitational field, And 2, it's generally covariant. I think condition 1's kind of redundant, really, because we wouldn't be interested in equations that didn't hold anyway. Let's leave it there. Now, what does general covariance mean? It means it preserves its form under a general coordinate transformation. X mu goes to x prime mu of x. That's a profound statement, but it embodies everything there is to know about general covariance. Not quite everything there is to know about general relativity, because we have to augment this principle with some equations that the metric tensor obeys. But the principle says whatever equations we write down for gravity, or for gravity coupled to matter, or for light, or particles, whatever they may be, the equation has to be the same in all coordinate systems. So I can take any old x, go to any old x prime, and the equation should look the same. So let me just elaborate on that. 2 guarantees if the equation is true in one system of coordinates, it's true in all. And you could, I guess, to justify one, says that the equation is true in locally inertial coordinates. And hence in all. Now, how do we achieve this? How do we ensure that our equations are the same in all frames of reference? Well, that's the topic of geometry, and it's what we're going to do now. But just to conclude this first section on the motivations for general relativity, it has to be acknowledged that they were almost exclusively theoretical motivations. There was no experimental results forced Einstein to invent general relativity. There was this anomaly in the perihelion shift of the planet Mercury. I suppose you could call that something that was a clue that all was not right with Newton's laws. But Einstein, that wasn't Einstein's motivation. He didn't say, I've got to invent a new theory because of the planet Mercury. He said, I've got to invent a new theory because Newton's laws are incompatible with special relativity, and I want to incorporate the equivalence principle. And he was inexorably led to a geometric description of gravity in which the metric tensor, g mu nu, will play the role of the gravitational field. So these were all theoretical motivations, and only afterwards was his theory confirmed by the experimental results. He accounted for the anomalous precession of Mercury and for other effects too that we'll be talking about. Yeah?
So the equation, the second derivative of psi with respect to s is equals to 0 on the top board, on the top right board.
Yeah?
There, yeah. Well, so that only has to be true locally, according to equivalence.
Yes.
Right. Did we use it somewhere? Or did we use the fact that it's only true locally?
Good question. It's sort of implicit. I mean, what we've done, this quantity gamma is not a tensor, okay? So it will change. It can be 0 in one coordinate system and not 0 in another. And what we're saying is, locally, we can put it to 0, which is what we're doing when we write that equation. So it wouldn't be valid globally. So I've implicitly assumed locality by assuming that there's an equation that obeys the rules of special relativity. So that brings us to the end of the first part of these lectures, which was the motivation for Einstein to come up with a new theory and why the new theory was one of geometry. So now's a good time to pause and ask any more questions before we devote ourselves to more details of this geometry. Okay? So here we go with geometry.
We require the equation to hold without gravity. But
I'm sorry, the board was noisy. Could you start again?
We require the equations to hold without gravity, but in reality, we never actually get that case. There's always some gravity there. Does this make a difference in the theory that 0 and a very small number can give a very different result? If gravity is something large and something very small, you still can get a result.
Yes, you're right. We can never switch gravity off. It's always there. Except locally in free fall. That's the best we can do. When we're freely falling, then at least in a small region of space-time, we switched off gravity.
But even then we haven't, because there are still forces from everything around us, right? We're never actually freely falling. We're never actually isolated.
No, we can never actually switch it off. That's right. So special relativity is never really valid in any global sense. But to a good approximation, for most practical purposes, if you're doing a particle experiment at CERN in the Large Hadron Collider, you can forget about gravity. But it's still there. You'll get the right answer just by using that equation. It's a very good approximation. So when we say in the absence of gravity, it's an idealization. There's never an absence of gravity. Yes?
Right almost behind you, the geodesic equation.
Yeah.
Where's the equal sign that makes the equation?
Sorry. Glad to see you keeping me on my toes. Any other questions? Yeah?
So I just want to compare these two equations. One is that, the other is the geodesic equation. So do you mean for first equation is locally applicable but not globally? And you get the first equation because it's Lorentz invariant. And for the second equation, you get it from doing this variational principle. You get it, and this is global.
Yes. And the remark I made about the affine connection being 0 in one case, not in the other, I'll return to that issue when we've done some more geometry. Yes?
And the expression for the integral that we use to derive the affine connection in terms of the variational principle, can you talk about just what it is that you used as your ds by dt?
What I used?
Yes, the expression for it.
For what, sorry?
For the ds by dp in the integrand. What precisely did you put in the square root? I see that the g's are numeric, but why did you make that substitution? Why is the square root the ds?
The idea is to make the Lagrangian Lorentz invariant. All right, that quantity has to be Lorentz invariant, so you have to parameterize it by some quantity, and that's dt. But p, which is the one parameter family of curves he's describing there, and then you write it in terms of new coordinates.
You know, in order to get this equation, I need to vary g.
Is it right?
So I swap ds by dp for something involving g, so that the variation of g will enter into the variational principle. And in this combination, I don't want to give the game away because this is your exercise. This combination will appear in the variation and lead to this equation. But it's in Weinberg's book if you get stuck. Okay. So 2 is what we call differential geometry. And 2.1 will be tensors. Now, if the physical requirement going into this is that the laws of physics should stay the same when we transform the coordinates. So if we're to stand any chance of doing that in a systematic way, the physical quantities we're interested in should transform simply under some change of coordinates. And tensors are objects that have simple transformation rules. And the simplest example of a tensor is a scalar. And under an arbitrary transformation of the coordinates, x goes to x prime of x, a scalar field is defined to be one for which the new scalar field as a function of the new coordinate equals the old scalar field as a function of the old coordinate. So that's the definition of a scalar. Vector come in two kind, contravariant and a contravariant vector will be denoted by some symbol with an upper index mu, and it says the new a mu in the new coordinates is equal to the old a nu in the old coordinates but with a factor dx prime mu dx nu. An example of a contravariant vector is the infinitesimal coordinate differential dx prime mu dx nu. That transforms as a contravariant vector. Note x mu itself is not a vector. According to our definition of the vector. Now, in addition to vectors with upper indices that are called contravariant, we have vectors with lower indices which are called covariant. And the covariant vector which I've decided to call B mu has a lower index, and the new vector in the new coordinates equals the old vector in the old coordinates times dx mu dx prime mu. So you see it's the other way round to the covariant case. And an example is the derivative of a scalar d mu phi, or in our new notation, phi prime comma mu of x prime. And here you should bear in mind that if it depends on x prime, the comma mu refers to derivative with respect to x prime mu is dx mu dx prime mu d mu phi of x. Sorry, phi of x comma nu. So the derivative of a scalar is an example of a covariant vector.
It looks like on the right-hand side of that equation, there's a d nu of x prime. Is there supposed to be prime in x?
I'm sorry? Oh, no prime, thank you. Don't know if that was a prime or a smudge, but it shouldn't have been there. Well, having done scalars and vectors, it's then straightforward to do tensors. And scalars and vectors are special cases of tensors. And a tensor of rank R has P contravariant indices and Q covariant and R is P plus Q. So it would be represented by something with T, mu, rho, bunch of upper indices, p times, and then alpha, beta, gamma, bunch of lower indices, q times. And the transformation rule for a tensor is just an obvious generalization of what we did for vectors. Namely t prime mu mu. Let me just do it for rank 3, and then you can fill in the rest. Is dx prime mu dx rho dx prime mu dx sigma dx mu dx prime lambda t rho sigma. Sorry, that should be not a mu, but a kappa. Mu, nu, kappa, rho, sigma, lambda. And that should be a kappa. So the rule is, if there's an upstairs index, it follows the same rule as a contravariant vector index. If there's a lower index, it follows the same rule as the covariant vector. So this is the general rule. It's often convenient to ask what happens for infinitesimal changes in the coordinates. So x mu goes to x prime mu of x, where the new coordinate differs from the old one by epsilon mu of x, and epsilon is small. Infinitesimal, in other words. So delta x mu is epsilon mu of x, if you want to write it that way. And the question then is, how does the tensor transform? But here, notice, we define the symbol delta to mean t prime of x minus t of x, not t prime of x prime. So how do scalars, vectors, and tensors transform infinitesimally? So if phi prime of x is phi prime of x minus epsilon, which is phi prime x prime minus epsilon, which is phi prime of x prime minus phi prime comma mu of x prime epsilon mu, which to first order in epsilon is phi of x minus phi comma mu of x epsilon mu. So delta phi of x is minus phi comma mu of x epsilon mu. That's how a scalar transforms infinitesimally. involves its first derivative. Just a comment. Some authors prefer to call what I've called delta bar to distinguish between t prime of x prime minus t of x. So some authors prefer to call that delta and to call that delta bar, but we'll use the delta. So we can now work out the infinitesimal rule for a contravariant vector. And it looks like minus a nu of x, sorry, a covariant vector. Epsilon nu comma mu minus a nu comma nu epsilon nu of x. And then we can generalize to our arbitrary rank tensor. Let's do it in the case of rank 3. It's t rho nu lambda epsilon mu comma rho plus t mu rho lambda epsilon nu comma rho minus t mu rho epsilon rho comma lambda minus t mu lambda comma rho epsilon rho. So there are as many terms involving the derivative of epsilon as there are indices, and then there's always one term where epsilon doesn't get differentiated. Now, according to our definition, delta commutes with differentiation, so the variation of the derivative of the tensor is the same as the derivative of its variation. These infinitesimal mappings are sometimes called gravitational gauge transformations. Why? Well, in Maxwell theory, we have a gauge transformation is one which you can express on the variation, an infinitesimal variation on the Maxwell potential. And here the parameter is a scalar field for electromagnetic gauge transformations. Gravitational gauge transformations, the parameter is a vector field, epsilon rho. Remember, I said x mu is not a vector, but the variation of x mu is a vector, delta x mu, or epsilon is a vector. Any questions? So let me give you another little exercise. show that the G mu nu that we defined before transforms as a tensor second rank symmetric tensor. So what does that mean? It means G mu nu prime of x prime is dx rho dx prime mu dx sigma dx prime mu g mu g rho sigma of x. Which is equivalent to minus g mu rho epsilon rho comma nu. You've probably gathered by now that general relativity is all about indices, bunches and bunches of indices. You have to keep track of them. So it's a tensor. What is not a tensor is the Christoffel symbol. How does that transform? Well, there's a part that looks like a tensor, dx prime lambda dx rho, dx tau dx prime mu, dx sigma dx prime mu, gamma rho tau sigma of x. So if that were the whole story, it would be a tensor, but that's not the whole story. There's a term dx prime lambda dx rho d2 x rho dx prime mu dx prime mu. So this is a tensor. This is not a tensor. And that's important because why are vectors and tensors occupying our attention? It's because we want the laws of physics to be the same when we change coordinates. And the easiest way of ensuring that is to have quantities that transform in a simple way. And if you can write your equations in tensor, if your equation is a tensor equation, it means if it's true in one coordinate system, it's true in all coordinate systems. So we're going to have to be careful that if we use gamma, we do it in a way that preserves that property. The fact that it isn't a tensor means you can change its value by going to, if it vanishes in one coordinate system, it needn't vanish in the other one. And you can see here how a coordinate system x for which gamma vanishes is one for which the affine connection looks like it did in the freely falling system. So your gamma and my gamma can change, but if we have a tensor equation, the vanishing of a tensor in one coordinate system guarantees its vanishing in any coordinate system. And that's what we need to fulfill Einstein's principle of general covariance. So that's all for today. I welcome any more questions.